Hi, I'm Elisabeth Hendrickson.
I'm Joel Tosi.
I'm Chris Pipito.
Joel and Chris and I have a hands-on workshop that we've been teaching called Engineer Your System. This recording is just the lecture portions of that hands-on workshop, and in it we're going to introduce 3 system thinking tools: variability using Shewhart charts, causal modeling, and U-curves. You're going to see how these 3 tools can be used together to think more holistically about the system in which you live, and we hope you find this useful.
So let's talk about systems thinking. Think back to the run on toilet paper at the start of COVID. Everyone remembers lines wrapped around stores, empty shelves, toilet paper being one of those highly sought after items. People were buying extra toilet paper, not knowing how long it would be before they could purchase it again. And this strain on the system led to decisions from store managers to limit the amounts that people could purchase, and to order in excess to meet that demand. However, there's always this time delay between new orders placed and new inventory available. And eventually all the excess orders were delivered. We ended up with bulk packs of toilet paper that once were limit 1 per customer were now three packs for $1. So the systems are dynamic living things, and systems thinking is about making sense of complexities of those holes in the relationships in the system. So things change quickly, things are getting harder, and despite our best efforts, the policies we're putting in place are actually causing the most pain. And it's important to understand that we are embedded in systems that mold our behaviors, often in ways that we may not even like. But it's up to us to first understand the system as best we can and design systems that enable us to do really great things. So when we develop products or deliver services, there are countless interconnections that influence the outcomes we get. There are decisions we make and decisions others make that steer our systems, and the outcomes of those decisions are rarely linear or obvious. Systems thinking gives us a way to understand these relationships and put us in a better position to steer our systems with intent. And now over to Joel for some variability.
Thanks, Chris. We are going to start off with one of our favorite tools that help leaders see what's happening inside their system and see the impacts of some decisions. Variability. Start off with a quick story for you. If you're not familiar, the picture here is from O'Hare. So I live in Chicago. This is O'Hare Airport. It seems like a simple question. I have a flight coming up. When should I leave to catch my flight? Well, I'll give you 2 examples. On one Sunday in November, I was flying from Chicago to Winnipeg. I left my house 5 hours early, and I had to run to the airplane to catch it before the doors closed. 5 hours on a Sunday. The following summer, in August, my family, so myself, my wife, and our 3 children were going to Rome for vacation. We left our house at 4 hours before our flight to Rome on I think it was a Tuesday morning, and we sat at the gate for 2 hours. So on a Sunday, me flying by myself, I barely made it in time, but on a Tuesday, my whole family, we sat at the gate for 2 hours. So answering this simple question, when should I leave, is difficult because, well, there's a lot of variability in that decision. Some of it we can control and some of it we can't control. This directly gets into what we see in software. When people ask, like, when will it be done? Or what's happening when we're delivering software? There's a lot of variability in how we deliver software. So while we're going through this topic around variability, think about what it is to you and where do you actually see it inside your organization. I think what's interesting about this is many teams feel it, but it's hard to capture. You'll hear teams talk about thrashing, or they'll say it used to work this week or last week and now it doesn't work. But there's systemic causes of this variability that goes up and down. But how do we actually go about capturing it so it's more than just a feeling? I gave you that example with O'Hare. When should I leave for my flight? But in software, we talk about when will it be done? In this very real example, we have a team here that is delivering on average 5 story points per sprint. And so if we were to ask them, when would this team be done with a 40-point backlog? Well, the average says it should be 8 sprints. But if we look at their trends, we'd figure out that it wouldn't actually be done until the 9th or almost the 10th. And so even this question, when will it be done, and we're using averages, doesn't give us the right answer, but it also doesn't tell us what's affecting the team's ability to deliver. If we look at another team, same average, right? They have an average of 5 points. But if you're in a team having this type of experience where we get a little done, a little done, a lot done, a little done, a little done, a little done, a lot done, the experience for the team is very different. Some days it feels like they're grinding against a wheel, and some days it feels like everything's working for them. Same average, different stories. And as leaders, we need to know more than just the runs. We need to see what's happening and how much variability is existing so we can make better decisions. How do we go about seeing variability? Well, I have to have my Deming quote here for you, that understanding variation is the key to success and quality in business. For any leader, whether it's manufacturing or software, we need to understand variation. We need to understand it so that way we can actually see, so we don't overreact to noise, and we actually look at what's causing variation if we're not comfortable with it. How do we go about seeing it? Let's jump into it. This gentleman here is Walter Shewhart. So we're going to look at process behavior charts, also called Shewhart charts. When Shewhart created these charts, it was simply meant to be a statistical tool to separate signal from noise, so we could see the common variation that exists in a system, and then find out when there might be special causes that are causing outliers. But for right now, we just want to see how much variation is actually existing in our system. If you apply Shewhart charts to software delivery, which is of course what we're doing, think about it this way. The way we deliver software is a function of a system. That system is how we go about understanding the problem, to how teams work on it together, to how they build, to how they test, to how they ship. Everything is a function of that collective system. If we do nothing at all, a stable system will continue to deliver within a given range. It'll have natural variability. Our goal as leaders is to be able to see that variability and then use that variability to tell a story. Now that I see the variability, here's what's happening, here's what's causing it, and that's some of the stuff that we'll get into later in the workshop. How do we go about seeing it? Let's look at an example. In this example, again, right now we're just using story points and sprint velocity, something that everybody can relate to. In this example right here, this team is clicking along. Sprint 1, they have 20 points of work completed, sprint 2, 12, sprint 3, 32. And so you can see in this time series graph, we're just plotting their velocity sprint over sprint, and then an average bar in the middle. We set this up with our historical data so that we can see how much variability is happening. Now imagine we make a change, and in sprint 9, something happens. In sprint 9, the team completes 45 story points. Now, if we don't understand how much variability is naturally occurring, we might think that whatever change we made into sprint 9 is the cause of that success. We might celebrate something that really isn't a celebration. It's just naturally occurring variability. And if we made a change and now we say that was so good, all the teams follow, but then sprint 10 happens and only 5 points gets delivered. Now we don't know, should we tell all the teams to undo what they just did? Or are we just overreacting to natural variation? Again, if we don't see the variability, then we overreact to noise. As soon as we introduce these process behavior charts and these control limits, we see the variability that's inherent in the system. So in the next slide, you can see what we've done is we've added this yellow bar at the top around 65-ish, and there's a green bar around 0 if you really can't see, and that's the lower limit. So again, the green bar around 0 is the lower limit. The yellow bar is the upper limit. If we got into the math of it, the green bar would actually be below 0, but for all intents and purposes, we're not going to have a team velocity below 0, hence we set it at 0. So now what we can do is, using the historical data of this team, we can see that On any given sprint, a velocity between 0 and 65 would be completely expected because that's how much variability is inherent in their delivery. It's not good or bad, it's just the facts. Now, once we see this, if we're not comfortable with that amount of variability, then we could look at the underlying causes of variability and make different decisions. But the goal here is to see the variability so we don't make rash decisions. Say that 3 times fast, right? So again, we use the control limit charts to see the variability that's inherent in a system. The example we just walked through is not just about velocity. Having done this with numerous organizations, I can tell you from a marketing perspective, and if you're looking at conversions and sales rates and are our product ideas actually making a difference, the same technique applies. If you want to understand bugs and how many bugs are being introduced, it's a function of the system of your work, and you can look at the variability in your bug discovery rates. Same thing with stability of systems and work aging. This technique of seeing how much inherent variability you have in your system works across a number of metrics, and it's a key tool for leaders to use. If you want to do this, create these upper limits on your own, the formulas here, I'll walk through for you briefly, but look, you can also do this very easily through Excel. If you remember in those early slides, the first thing you do is plot your data over time, right? So you have a time series, you plot your moving data over time, you calculate the average, and you plot that in the middle of the graph there. Then you need to calculate the moving average. The moving average is the absolute value of the difference in 2 data points. Sprint 1 to sprint 2, sprint 2 to sprint 3, sprint 3 to sprint 4, the absolute value of those differences, and then you divide it by how many deltas there were. That gives you the moving average. Once you have the moving average, you calculate the upper and lower bounds by applying a constant and multiplying it by the moving average, and then you add that and subtract it from the average. Or if you want, you could just apply 3 sigma to the average and you get your 99th percentile. The goal here is really you see how much variability exists in the system. Anything outside of it is special cause, but we can see like this is naturally occurring variability. This is what's happening right now in our system, so we don't overreact. Questions from my audience?
I'm really curious. So, can you give us a concrete example that you've seen in the real world where maybe a team was just looking at the events and not really seeing the pattern of variability and therefore making less than great decisions?
Yeah, it's a great question, Elisabeth. I think the most common pattern I see, um, Agile gets a weird rap these days, right? Because people didn't do it right and this and that. What I think happened is actually something a little bit different, and I think it actually ties into variability. I think the pattern I see a lot of organizations is they start off tried and true, and they'll say, we're estimating story points, and it's about value. And so then all of a sudden, a team has again a variability in their delivery rate. This sprint they got 15 points done. Next sprint they get 25. Next sprint they get 0. Next sprint they get 3. And then what happens is, and this has happened in numerous organizations I've been in, somebody wants to control it and say, why is there so much? Why does your velocity go like this up and down? And then the team will say, well, because we found bugs late, or the requirements weren't quite right, or I had to fix something, or I had to document something. And so then what happens is, which I think is a natural reaction, is uh, leadership wants to say, I need the velocity to be more predictable. And so what happens is the team then changes what the stories mean. And then they start creating stories for the bugs. And then they create stories for the documentation. And they create stories for this. And now all of a sudden, the velocity starts to flatten out. But it tells a different story. And it's because people, they see the variability and they don't look at what causes it. They react to it. And so they're trying to control it. Another favorite one I have, which I know we could all relate to, is always around testing. a team is finishing their shipping to lower environments, and they're checking off the box and they're saying it's done. But when they get to the lower environments, the environment isn't quite right. Their dependencies are the wrong version, or the data changed, or something wasn't deployed. And so that's inherent variability in the environment. But what we see is the thrashing of the testing, and we're blaming testing for inherent variability in the environment. And I think that's what we got to see is like the variability is telling us something. It's not telling us the tests are bad. It's telling us this environment is a problem, right? And so we got to see the variability so we make better decisions.
Excellent. Excellent. Yeah. So trying to see these things. Let's talk about causal modeling and doing that, and the constructs that we have in our minds and shape the experience of the world around us, our mental frames, and causal modeling helps get those things out. So in that thought, I wanted to share about how like systems are these nonlinear things. And to share an example that I'm going to talk about this no deployment Fridays. An organization I was working with had a few bad deployments on Fridays, and a rule was implemented. We just don't do that anymore. It wasn't that Friday deployments were worse than Tuesdays or Wednesday deployments. They were all bad. It just felt more bad because it was the weekend. So this fallacy of thought in simple cause and effect is around like just because A happened before B doesn't mean A caused B. So the cause and effects are really often separated and like there's time and space that happens around these things. And that makes simple attribution, doing something like simple attribution becomes dangerous. So what often looks like cause and effect, deployment on Friday, failed deployment, may actually be two or more effects of deeper causes. And these events kind of start to arise from these complex relationships. So apparent movements might be due to natural oscillation or variability rather than our own interventions, or improvements could be due to our interventions in other areas of the system. So for example, here, to prove a point, when with that team, we did a release on Friday the 13th. We attached an image of Jason from the movies to the required release plan, and magic happened. In reality, what was going on is we spent time improving deployment scripts and got better at testing and making tests less flaky. And that led to, increased deployment being better, and everything was better for everybody there. So more about this is like it's a linear open loop thinking that doesn't consider the interconnections of a larger system. And another example I'm sure we're all familiar with is a mental model that we often see here with projects or products that go through these phases, and that these phases have a beginning, a middle, and an end. I've never actually experienced this being true yet. There's always feedback and iterations we got to go through, because inevitably we find out that we really didn't understand the problem, or maybe the tech, or even the people we're trying to help. So we got to start to think about systems and viewing them in the cycles that they run in. And when you're often stuck in open loop thinking, we think that we know our goals. These goals motivate the decisions we make. Those decisions drive actions that change the state of our system. Perfect. Problem solved. But that's actually wrong. We cannot know what decisions to make based only on where we want to go. We also need to know where we currently are. So we need this like feedback in the system to let us know if we're moving towards or even achieving some of these goals we want. And that seems simple enough, but this is just our mental model of the system. There are these unintended effects of what happens in the system based on the decisions we make and the actions we're taking from that. And these unintended effects typically feed back in the opposite direction of what we're trying to achieve. So, and again, this only being our mental model of the system, there are others doing the same thing as us, right? They're making decisions that drive their actions that impact the state of the system as well. These also typically drive the system in the opposite direction of our goals and have their own unintended effects. So now this is a pretty complex thing to think about and try to manage through. So it helps to know that when we're mapping, the map is not the territory, but it does help us kind of navigate it a little bit better. So the stories we talk about and systems thinking in general is about expanding the boundaries of our mental models so we can take into account other parts of the system when trying to make these decisions. So the model is not the real system. The things in our heads are filtered interpretations of the system. And this is kind of giving us a view into, the models that we walk around with. The models that we do create, they don't give us answers. They just give us insight. That insight we need to then use to improve the model. So with causal modeling, we have a few ideas to work with, all centered around seeing the same reality and telling the story. Joel shared a story earlier about a team's reaction to velocity and some of the decisions they were making. So the question that they had was, why is the velocity going down? So once we know the question, we can then start by listing out some of the nouns or the variables of the system. And when we have those, then we have these arrows. And these arrows are the links of the causal relationships. They show that as a change in the first variable happens, it results in a change in the second. So these nouns kind of change over time, either increasing or decreasing, depending on the relationship between them. We'll use plus symbols to show amplifying relationships that go in the same direction. So if you're reading this, if the pressure to do work goes up, bugs goes up. We'll use a minus or a negative symbol to show dampening relationships that go in the opposite direction. So reading this again, we could say as the bug count goes up, the velocity goes down. We also have this idea of a two-tone box as a decision point, somewhere we can make a choice. These choices are typically where human intervention is causing the variable it's connected to move in the same or opposite direction from the originating variable based on the intervention that we make. So in the story that Joel was sharing, we chose to apply pressure as we reacted to the velocity being down without seeing the natural variability in the system. And by applying pressure to do work, we increase the amount of bugs and the velocity keeps going down. So we have our circles and clouds here, the nouns or variables of the system, changing over time. The links are the relationships between them, amplifying or dampening their connections. And this whole idea of causal modeling is about making visible the normally invisible threads that connect the system. So we're mapping the ways the parts of the system influence one another through feedback loops that either reinforce or balance the system. All systems are made up of these two types of loops. These examples come from an experience I had. I was working at a mortgage lender and we were doing quarterly releases. I'm sure everybody's kind of had that experience at some point or another. But the final 2 weeks of each quarter, we'd get into war rooms. And these war rooms were there to kind of handle the bugs and the merge conflicts. So once we resolved the bugs and the merge conflicts, enough for the release to actually happen, we'd return to working separated until it was time to war room again. So we had both balancing loops and reinforcing loops happening. So if we're looking at the balancing loop, as the bug count increased, our war room effort increased, and the amplified war room efforts reduced the bug count. So that's like a little balancing loop that was going on. It's seeking stability and to bring the system back under control. And if we look at the other loop, the more we worked apart, the more merge conflicts we would get. And that's just reinforcing all the way around. That cycle just kept amplifying itself, leading to more and more complex integrations. So balancing loops seek stability and self-correction. Our reinforcing loops are continuously amplifying cycles. These cycles could be good or bad, virtuous or vicious. This is a vicious cycle. In software, we have all kinds of loops. Most of them we don't see or know about. If we walk through this one, and we can start at this idea of pressure to do work. If pressure to do work is up, then the amount of concurrent work we have going on is also up. As the amount of concurrent work is up, our system quality goes down. As our system quality is down, our customer satisfaction is down. And when customers aren't satisfied, we have more pressure to do work. So we've walked through balancing and causal models and balancing and reinforcing loops, the connections they make in all of their relationships. And I'll throw it out to you watching this. What type of loop is this?
Great question, Chris. I think we all see this and experience it and feel it all the time inside software. If I heard you correctly, Pressure to do work going up increases concurrent work decreases system quality, decrease in quality decreases customer satisfaction, which then increases our pressure to do work. If I started off with increasing pressure to do work and I come back and I'm still increasing, it feels like it's a reinforcing loop. Do I win the prize?
Yeah, yes, you do.
Thank you.
That's exactly the way that you read it perfectly, exactly the way it plays out. Yes, it's a reinforcing loop, and there's a little trick to know about it is that when you're looking at these models, if you have an even number of negative links, including zero, that's a reinforcing loop. So naturally, an odd number of negative links would be a balancing loop. So here we see the two minus symbols, even number, it's reinforcing.
Yeah, this is great. Do you have another example of either a reinforcing loop or a balancing loop, or just interesting insight you've had from a causal model with a team you've been with recently?
Yeah, actually, that's a really good question. I had to think about that for a minute. Um, I had one where we were trying to answer the question of uh, why things are wrong. You know, the things we deliver are wrong. So we tried to model out why we're wrong, and pretty much where we ended up is we ended up finding out that the more bad ideas we had, the more bad ideas we deliver, and the more bad ideas got delivered, the more dissatisfied our customers were, and the more dissatisfied our customers were, the less they would engage with us.
Yeah,
So then we just had more bad ideas to work off of, and around we went.
very relatable.
So then, Joel, back over to you to kind of talk us through some modeling and variability, if you could.
Yeah, most definitely, man. Now that we've been able to see variability with a team, and now we have this idea of how to model it, a natural reaction a lot of leaders have is, I want to I want to control variability. I want variability to be zero. I gave that example early on around changing the definitions of stories and how that actually was hiding the truth. Many leaders also don't hide the truth, but they want to then say, I don't want variability. It makes me feel uncomfortable. It's a very important thought exercise for us to go through, is like, what would need to be true for us actually not to have any variability? Well, as Chris alluded to, we'd have to have engaged customers, and we'd have to perfectly understand what they wanted. They would have to give us the perfect requirements, and the people that get the requirements would have to perfectly translate them to the people doing the work, and we all understand it perfectly, and the code would have to be perfect and beautiful. And then maybe then we wouldn't have any variability. But that's not really true, because if we had that much consistency, then keep in mind the things also that couldn't change. We couldn't change tech, because that would introduce variability. We couldn't go from on-prem to the cloud, or we couldn't go to from manually provisioned to automated provisions infrastructure, because that would be changing things and potentially introducing variability. We also couldn't be innovative, because innovating would be deviating from perfect requirements and perfect understanding. We couldn't explore, and learning would be bad, because to learn, we'd have to try different things to actually see what works and what didn't work. And so I bring this all up because it's a natural reaction to say variability bad, therefore stop it. But so much would have to be true that the cost of trying to control variability would be out the window. You'd have to give up so much, and even then it would be impossible, because let's be honest, we're people and we don't have perfect understanding, let alone perfect code or perfect requirements. So please understand that we want to see the variability, but the goal isn't to clamp down on it. If we think about variability also in this lens from Don Reinertson's Principles of Product Development Flow, we could talk about the goal is never zero variability. The goal is to understand the impact that variability has on us. Now, if variability is cheap, and by cheap, like, imagine we are trying to find market fit, and it's cheap and easy for us to experiment. We're doing paper prototyping or quick mocks, and we're able to get quick feedback from customers. We want to exploit that variability, because it's cheap and we can test a lot of ideas at the same time. And the cost of exploiting it there gives us signal when we should invest more heavily. But on the right side of this value stream, when we've actually decided on what we want to build and we're trying to get in a customer's hand, variability is very expensive. And so it's not about having zero variability, but it's about minimizing the variability we have. It's about when teams feel like that they have friction because they're trying to build software, but somebody is telling them build it one way and an architect says build it a different way, but a third team says you can't do it either way. That's unnecessary variability. When we're trying to deploy and one environment is available here, but the data is not available there and the integration isn't there also, it's unnecessary variability that we could minimize. It doesn't solve the problem of variability, but it's expensive variability. So again, the goal is never zero variability in our system. It's to understand the impacts that a variability are having. Once we see it, we can then decide, are we comfortable with that much variability or not? And then we can decide what we want to do about it. Seeing the variability helps us see how much there is. The causal models helps us understand where it's coming from, and then we can make better decisions. I like to think about it this way. Seeing the variability helps teams understand and share their story. Without this view, leaders always have the best intentions and frequently act in the wrong area. They act where they see the problem and not the cause of the problem. And so we want to put these tools together to make better decisions.
Joel, you had mentioned something during this as you were talking through about how going for zero variability could impact our ability to learn things. Could you say a little bit more about that?
So in our industry, we frequently want to talk about best practices as if there is only one way to solve a problem. But like, we are creators and builders, and we know that there is numerous ways to solve problems. When we want to control variability, a natural response would be just follow the best practice. Well, for example, you have to have code coverage of 80%. That's the best practice. Well, if I stop understanding the value of a good test and I'm just going for like that number, then I've stopped learning. I'm just kind of rotely going through the process. And I'm not saying, is this test actually helping inform me of something? Is it actually making me more confident? Is it actually making me feel more better? And I've stopped thinking about how to do the work, and I'm just reacting to like getting it done. Follow the standard, follow the best practice. And so that's what I mean by, when we want to kind of control variability, we tend to make these reactions to that stop people from learning and thinking, and they just kind of shut off and follow the rote process. Good question, man.
I want to talk about a third tool. So far, we've seen two tools. We've seen Shewhart charts for examining variability, and we've seen causal models for looking at the connected web of relationships within a complex system. And this third thing is really about finding the right decision within a decision point. A causal diagram can help you find the decision points, and U-curves, thinking in terms of finding the sweet spot, can help you figure out which way that decision should go. So some examples of trade-offs that we typically see in software. One might be the frequency of deploys. Now, the DORA research tells us that elite organizations are able to deploy multiple times a day, but not all organizations are elite, obviously, and in an organization that has not yet gotten to the point where it is safe to deploy that many times, there might be a push and pull between let's deploy less frequently so that we destabilize the system less, versus let's deploy more frequently so that we can get the value out of the work that we have done so far. And this can be a hot topic of debate in some organizations. Another example might be, how busy should we keep people, the level of utilization, how much slack are we going to allow in the system? And unfortunately, a lot of people think that zero slack is the right answer. We'll talk about that. The decision timing, when should we be making decisions? On one side of the spectrum, if we act prematurely without having data, we might make terrible decisions. But on the other hand, we can get wrapped around the axle waiting to have perfect information. And by then, time made the decision for us. We might have the frequency of when we run expensive tests like performance tests or security penetration tests. We might have debates about how much of our time do we invest in paying down technical debt. We could have debates about the frequency of dependency upgrades. You see that each of these, there's this debate, and oftentimes those debates end up kind of anchored at the extremes of the spectrum. Let's talk about the happy middle. So what we're really looking for is, where is the sweet spot between those extremes? But the question is, how do you find a sweet spot? And that is where U-curves come in. So let's take, as an example, batch size. This is a classic example from manufacturing, where we can look at data and charts that show us this U-curve relationship. It still applies to software. Your batch size in software is directly related to the how often do we deploy, or how big a change set do we merge at a time into our source control system. Your batch size is in software is really related to the number of changes that you are pushing out into wherever that's going. Now, in manufacturing, Ford W. Harris wrote a paper in 1913 called "How Many Parts to Make at Once?" And he had actual data to show the relationship between the drivers of the two ends of the spectrum on the debate. On the one hand, you've got the holding cost of the more inventory we have, the more we have to store, and there are holding costs associated with that. But on the flip side, so that's what happens if you have a lot for a long period of time. We have to pay to store that stuff, and there are depreciation costs and other costs associated with that inventory. But on the flip side, if we only make one at a time, the setup costs are huge. And so, because we would be, if this is about manufacturing, we would be setting up a machine in order to stamp out one thing. And we do all of this setup, we stamp out one thing, and then we tear it all down, and then we set it up to stamp out a different kind of part. Not very efficient. So he was able to show that the relationship, if we add these things together, we see a total cost, and there is an optimum point on that total cost that for your particular situation, you could calculate and say the optimum batch size for this part at this factory, given this process, is we make 100 at once, or whatever it is. So that's an example of a U-curve for batch size. Let's say it's 1991, and the standard way of building software at the time was to do a big annual release. And it was typical at that time. You have your analysis phase and your design phase, and so you do all of this analysis up front. You build a gigantic market requirements document, and then you go into specifications and you build a gigantic technical specification. All of that is inventory. And there is this opportunity cost during the time that we're doing all of this analysis to specify all of these features. We're not building features, releasing them, and getting the value out of it. So that's our holding cost. And there's a whole bunch of other risks in software associated with holding costs, including things like if you've built a bunch of features there and have not released them yet, there is a risk that those features don't actually meet the market need. And if you've built a bunch of features off on a branch and that branch hasn't been merged yet in with main, there is a risk that it's never going to be able to merge. I once saw a team have to throw out 6 months worth of work. So the holding costs aren't just the opportunity costs. There's a bunch of holding costs, but let's just say that we've got a relationship that shows a holding cost like this. Then the transaction cost, well, all of those expensive tests, like maybe you have to do performance tests or security penetration tests, those are examples of the maybe per release costs that you might have. And so similarly to manufacturing, you can also kind of look at the relationship and find a sweet spot for how often should we release for your particular context. Okay. let's take another example that I said we would come back to, and that is the example of utilization. I love Tom DeMarco's book, Slack, Getting Past Burnout, Busy Work, and the Myth of Total Efficiency. And in it, he's got this image of the efficient slider puzzle. This is one of those puzzles where you move the tiles around and you're supposed to get them in order, 1, 2, 3, 4, 5, 6, 7, 8. And if you actually put 9 tiles in this puzzle, you can't ever solve it. And so it's a wonderful illustration of the myth of total efficiency. The thing that a lot of leaders look at, though, is that in software development, one of the biggest drivers of costs is salaries. And so you don't want to have people be idle, because that means that you're just wasting money, right? Well, not really. Let's take a look at some analysis that Pavel Brzezinski did on his blog, which we'll put the link to this in the show notes. It's a fantastic post, and it shows the relationship between cost and utilization. So our intuition may tell us that the more idle we are, the higher the cost is, but that's only true on one side of the equation. The reality is that on the other side of the equation, there's a huge cost of delay, because the busier people are, the more they are completely unavailable to handle things that come up that are urgent. So, for example, if you have a team of people who are 100% busy and in the middle of doing features for a release, and then you have a support issue come up or an incident in production, no one is available. Now you have to interrupt them. But if you don't interrupt them, the cost of delay goes up infinitely. That's the point of this illustration, that there is an economical optimal utilization that allows enough slack in the system that the system can be responsive to the current conditions. Okay, so now let's talk about, let's say you've got a trade-off. You have identified a trade-off in your organization and you want to model that as a U-curve. How do you go about doing this? It's very easy to talk about finding the sweet spot. And it sounds like this should be simple. It turns out it's a little more challenging than it seems, because you have to think hard about what you're actually trying to optimize for. So step 1 is state the problem. And this is actually harder than it sounds. Getting a really, really good problem statement will get you halfway to a solution. But a lot of times we end up with a problem statement that's like, we have variability. Only as Joel has shown you, by itself, variability is not a problem. So you want to be super clear about what actually is the problem. What are we observing today? And what do we wish were true? And what's the gap between those two things? Frame that as a problem statement. And then you move on to step 2. Step 2 is, what exactly within this problem statement are we trying to optimize for? You might be trying to optimize for cost. You might be trying to optimize for risk. Risk is really interesting to optimize for because it's invisible. It's really hard to tell how much risk you have at any given time. But this is what's going to become your y-axis on this graph. Then you're going to start identifying the trade-off variables. What are all the things that affect the thing you're trying to optimize for? Guess what? That's where causal diagramming comes into play. If you start building out your causal map, you're going to start to see where the things are that affect the variable that you're trying to optimize for. Now you describe 2 or more. 2 is enough, but you might have more relationships between the trade-off variables and that y-axis that contributes to the total. And then finally, you're going to use that to draw the chart. Chances are you're going to look at the chart and say that can't be right, and you'll iterate for a bit until you're done. So that's how you get your own trade-off models as a U-curve. Now, let's walk through this as an example altogether. Let's take the example of dependency updates. So here is a challenging situation for a lot of organizations. You're using third-party dependencies, or you're using open source libraries as a dependency. So there can be a tussle around how frequently to update those. The more we update them, the more we destabilize the system potentially. We may have some challenges with lack of tests that would actually show us when something in that third-party library broke in a way that is surprising and causes our system to have a failure. So how do we frame this as a problem statement? Let's say that we created the problem statement. Our code base relies on external dependencies maintained by third parties, and those dependencies are constantly being updated, and we struggle to keep those dependencies up to date. So that's our problem statement. Now let's go to step 2. What are we actually going to optimize for? Is it the cost, the overall cost of ownership of our system with respect to the dependencies? Is it the amount of time that it takes to get releases out or to make changes to the cycle time for stories? Is it risk? Let's say we want to optimize for risk, especially if we're talking about third-party dependencies. It is a common thing that we would want to optimize for, because the older those dependencies are, the higher the risk that there is a known vulnerability in them. And the newer the dependencies are, the higher the risk that they have, that there is a bug. Like kind of the rule in software is never take the 0.0 release of anything. Wait for the 0.01 to come out, because that's when they'll have fixed the bugs they found in the big release. So there is a risk that there are bugs that haven't been found yet that would affect how our system works. Okay, so step 3, we're going to brainstorm all of the factors contributing to risk. I just named a couple. There could be other risks associated with frequent or infrequent updates for your system. So we'll go on, say we've brainstormed all of the factors that contribute to risk. Step 4 is now we're going to concretely define those relationships. And that's where, again, it becomes really interesting, because we have this hazy notion about the relationship between the freshness of a dependency and bugs, or the staleness of a dependency and potential security vulnerabilities. But now we're actually going to write down something. We don't have to have numbers. If you have numbers associated with these things, then it becomes very easy to actually graph them. But in this case, we can just kind of sketch on it, like on a whiteboard, sketch the relationship between these things to draw the chart, so that we can see that if and again, this is just like a causal diagram, where age of dependency would be one of your bubbles, and number of security issues, known security issues, would be another bubble. And there is a positive correlation between those two things. And so that is the blue line on this chart. And the gold line on this chart is related to the age of dependencies and the probability of an unknown bug breaking something in our system. And there, that relationship is an inverse relationship, because the older the dependency, the less likely there is an unknown bug that we haven't discovered yet that would cause a problem with our system. If you had numbers and could add them together, you can see that the resulting shape of that, the sum of those two things would be the curve. And so this helps you at least have the conversation, the right conversation about the trade-off, so that you can say, we don't want to take the newest thing. We don't want to wait too long. And if you can quantify it, that helps you, but let's at least kind of pick a range of age so that we can have a policy and then iterate as we learn more. So we've now gone over 3 key tools in systems thinking: variability, causal diagrams, and U-curves. Let's talk about how you can use these to tell your story. And to this, I'm going to throw it back to Joel.
I wanted to ask you a question.
Yes.
When you're talking about U-curves, I loved how you framed it up. If you didn't have the data, you can still kind of at least get an idea, to see what was happening. In your experience, are people doing these U-curves in isolation? Are they doing them collectively? Like, tell me how is this actually working?
Yeah, most often I see that this is a collaborative conversation between stakeholders, and I find this to be a very useful way to write something down so that we can all point to it and be having the same conversation, instead of just having a position-based debate about the freshness of dependencies or the amount of risk that we're incurring about as a result of some other decision. So instead of having arguments about the edges, the extremes on that continuum, we're having the same conversation and are able to actually reason about trade-offs and find the perspective from which we have optimized for the thing that we really care about, but we're doing it collaboratively.
Yeah, I love it. Kind of like getting all the voices heard, and it's not about I win, you lose. It's about us together seeing the right options. So, as Elisabeth alluded to, these three techniques, the Shura charts to see the variability, the causal modeling to understand influences, and U curves to find the good happy mediums in between two extremes. These techniques are tools that you can use today. They help you see what's happening inside your organization. They help you tell what's happening inside your organization. And just as Elisabeth mentioned, you can point to some things and kind of say what's happening. And once you can tell your story and you see it together, you can then make the changes you want. Your story is, of course, unique. Your constraints are unique. Your organization is unique. In every organization, that story is, of course, shaped by constraints and very non-obvious forces. Just as Chris alluded to, non-linear kind of all of these influences. Our goal with these tools and techniques is that you can use them together collaboratively to act where the pain is caused and not where it's observed. That's what we want to see. And this is how we create better cultures and better organizations using these techniques. And with that, I thank you. Elisabeth, Chris, would you like to thank the audience also? We thank you.
Yes,
Thank you so much.
absolutely. Yeah, thank you all.